Ever wonder how AI models like GPT or BERT understand language so deeply? It's not magic, it's a revolutionary architecture called the transformer. Today, we're diving into the inner workings of transformers, unraveling the math, the mechanics, and why they've become the backbone of modern AI. Let's get technical. Before transformers, sequence models relied on RNNs and CNNs. But here's the catch. RNNs struggle with long-term dependencies due to vanishing gradients, and CNNs can't capture global context efficiently. Imagine trying to understand a paragraph by only seeing one word at a time. That's the RNN's limitation. CNNs, while good at local patterns, miss the bigger picture. Enter the transformer, a model that ditched recurrence entirely and embraced self-attention. Self-attention is the transformer's secret sauce. Let's break it down. For every word in a sentence, the model calculates three vectors: queries, keys, and values. Think of queries as what I'm looking for, keys as what's available, and values as the actual data. The dot product between a query and all keys gives a score. This determines how much focus each word should have. Then, a softmax normalizes these scores, and the weighted sum of values creates a context-aware representation. It's like having a conversation where every word dynamically references the entire sentence. But wait, how does the model know the order of words? Unlike RNNs, transformers don't process sequences sequentially. So, positional encodings are added to input vectors, embedding position information into the data. These encodings use sine and cosine functions of different frequencies, allowing the model to learn relative positions. For example, the fifth word's encoding is a unique combination of sine and cosine waves, ensuring the model distinguishes between cat sat on the mat and mat on the sat cat. Transformers use an encoder-decoder structure. The encoder processes input, building a rich contextual representation, while the decoder generates output step by step. Each has multiple layers of self-attention and feed-forward networks. The key innovation: parallelization. Unlike RNNs, which process words one at a time, transformers handle entire sequences at once, drastically speeding up training. Here's where it gets even more powerful: multi-head attention. Instead of one self-attention mechanism, the model uses multiple heads, each focusing on different aspects of the data. For instance, one head might capture syntax, another semantics, and another grammar. These outputs are concatenated and linearly transformed, allowing the model to learn diverse relationships within the data. It's like having multiple lenses to view the same information. Training a transformer involves minimizing a loss function using gradient descent. But with billions of parameters, this requires techniques like mixed precision training, distributed computing, and efficient memory management. Oh, and don't forget the Atom Optimizer. Its adaptive learning rates make training stable and fast. The result: models that can generate human-like text, translate languages, and even code. Transformers aren't just a step forward, they're a paradigm shift. They've enabled breakthroughs in NLP, computer vision, and beyond. But the real magic lies in their flexibility. Tweak the architecture, and you can build models for anything from drug discovery to climate modeling. So next time you interact with AI, remember, it's all powered by these elegant math-driven systems. Thanks for watching and stay curious. Want to dive deeper? Check the description for links to research papers, code implementations, and further reading. Like, subscribe, and hit the bell for more deep dives into AI's toughest concepts.